The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I know you all are now busy with your preparations for your online exam, and this is your first experience writing or giving answers online to your own teachers. And children, see, this is not just to make you panic or make you afraid of your syllabus. It is for you and also for the teachers to understand where you are, how far you are comfortable with the syllabus, or where are the areas that you need extra support. So these are the main intention for the online exam, the purpose of conducting an online exam for you. What you need to do from your side is, you will be getting the timetable. Excuse me, children. Once you get your timetable, set yourself a timetable for studying, for preparing for the topics which have been given for various subjects. See which are the areas you need to give more importance, and see where are the areas that you haven't understood clearly. Call the concerned teachers, get yourself clarified. So the best solution for a problem is to face it. So now it's going to be on November 2nd, our exams getting started, and I want you all to be on toes, and I know my children will do pretty well, because it is like how you prepare for the exam. Don't get stressed, put yourself gaps while studying for the exam, love the subject, and then you start preparing. Definitely things will be under your control. Okay, take proper food, take proper rest, and then you continue this. Okay, children, so wish you good luck, do well, children. Now let's get back into the topic for today. See, today I thought, like since we have started with dual behavior and hydrogen spectrum, we will also do some of the topics. That is, we will also do the problems which have been covered in the textbook. So when I am doing the problems, I want you to do the same thing in your notebook as well. The first problem we will do with hydrogen spectrum. It's in page number 45. If you can see problem 2.10, what are the frequency and wavelength of a photon emitted during a transition from N, that is energy level 5 to energy level 2, state in the hydrogen atom. So in the hydrogen atom, the electron is being, that is a photon is nothing but a light. So a photon is being emitted from energy level 5 to 2. So we know 2 energy level is nothing but Balmer series, that is in the visible region. So what is the formula we need to write? If you can write the formula, it is very important, children. What is given in the question to us, first we need to write. Given energy level initial is 5, that is a photon is jumping from 5th energy level to the 2nd energy level. This is what is given to us with respect to the question. They have asked us to find out the wavelength and frequency. We know the energy difference del E is equal to, this is R, this R value is different, 2.18 into 10 power minus 18 within bracket 1 by Ni square minus 1 by Nf square. That is energy, initial energy state minus final energy state, the square of it. So when I am substituting the value 2.18 into 10 power minus 18, open the bracket, write Ni is equal to 5. So 1 by 5 square minus 1 by 2 square. I get a value which is in minus, which shows there is an emission of energy, not absorption, there is an emission of energy by the photon. Now they have asked us to calculate wavelength and frequency. I have got my del E. How can I find out either my wavelength or frequency? We know there is a formula, del E is equal to h into nu, where h is my Planck's constant, nu is the frequency. So from this I can calculate the frequency is equal to delta E by h. Now delta E already I have got it 4.58. So I substitute here, I do not put the negative sign because we are not worried about whether it is emission or absorption, just put the value alone. So you get 4.58 into 10 power minus 19 divided by Planck's constant value 6.626 into 10 power minus 34. So once you put it, you get the value for the frequency. Write the unit in hertz. Never forget to write the unit, children, unit is very important. So I got my frequency. Now how will I calculate my wavelength? We know there is a relation between wavelength and frequency. Wavelength is equal to C by nu. So what is C? Since it is given photon, it is nothing but light. So we know what is the value for speed of light. Speed of light is 3 into 10 power 8 meter per second. And again nu we got it here 6.91 into 10 power 14. So once we solve it, we got 434 nanometer. 10 power minus 9 is nothing but nanometer. Children, some of you were having doubts with 10 power 8, 10 power 2, 10 power 3. Use a scientific calculator so that you get the values properly. Scientific calculators you are supposed to use, not an ordinary calculator. Please understand, children. So this is how we will do the first problem. Now we will get into the second problem now. Children, the second question was calculate the energy associated with the first orbit of He plus and what is the radius of this orbit. See, I have told you Bohr's atomic theory was helpful in finding out for He plus, Li2 plus, where there is only one electron in the nucleus, that is in the orbit. So first with He plus I know my n is equal to 1, number of electrons equal to 1 and atomic number is 2. What is the energy? En, that is for n equal to 1, 2, 3, it is minus 2.18 into 10 power 18 into z square by n square. Again this formula, please write it as important. Why I am giving the formulas now is when the problem is solved, you will know which formula you should use for which problem. So this you will use even if Li2 plus is given, n will be equal to 1 but z will be equal to 3. So for that purposes you will use this formula. So for n is equal to 1, E1 will be the same value minus 2.18 10 power minus 18 into z, atomic number is 2 here, so 2 square by n is equal to 1, so 1 square. Once I solve it, I get the value of E as minus 8.72 into 10 power minus 18 joules. Now how do I calculate my radius? To calculate the radius, the formula given is, you know, 52.9, it will be given to you in the textbook. So I am just converting into nanometer. So please use this when you are doing your problems. 0.0529 nanometer into n square by z. Again this formula you should remember to find out the radius. Here n is equal to what? N is equal to 1 and z is equal to 2. So substitute the value for n and z here, you will get the answer for your radius. For radius, r is equal to 1. For 1 electron, the radius of this orbit is given as 0.02645 nanometer, which is 10 power minus 9 meter. I hope you understood. Now we will do some de Broglie's problems and then we will get into Heisenberg's uncertainty principle. Okay, let us do some of the problems from the de Broglie's relationship. What is the formula here? Lambda is equal to h by mv. Now the first question given to you in the textbook was, what will be the wavelength of a ball of mass 0.1 kg moving with a velocity of 10 meter per second? So mass is given as 0.1 kg, velocity is 10 meter per second, you need to find out the wavelength. So what is the formula? Lambda is equal to h by mv. What is h? 6.626 into 10 power minus 34 Planck's constant divided by mass is 0.1 into velocity is 10. Once you substituted everything, you get the value for your wavelength and write in meters. Understood, children, now? So this is how you will calculate the wavelength of the ball. The next question is the mass of an electron. Mass of an electron is 9.1 into 10 power minus 31 kg. And its kinetic energy is 3.0 into 10 power minus 25 joules. Calculate the wavelength. Before calculating wavelength, we need to calculate the velocity, because you need to substitute in lambda is equal to h by mv. How do we do it, children? We know kinetic energy is half mv square. From this I can calculate my v. V will be 2 into kinetic energy by m and the whole power half, that is square root also you can take. So when I substitute everything here, the whole power half, I get my answer as 812 meter per second. Put 2 into kinetic energy value 3 into 10 power minus 25 divided by the mass of electron you put, you get the value for the velocity. Now we know what is the formula for lambda. Lambda is equal to h by mv. So we know what is h. Mass is given in the question, velocity we just now find out. So with everything you can calculate the value for the wavelength. So once you got the wavelength, you know what is the answer, that is 896.7 nanometer, or you can convert, you can put 10 power minus 9 meter also, both are correct. The third problem is calculate the mass of photon with wavelength 3.6 Armstrong. 1 Armstrong is 10 power minus 10 meter. So it is 3.6 into 10 power minus 10 meter. So again rearrange the formula, lambda is equal to h by mv. We know m is equal to h by lambda v. We know what is h, divided by lambda into v. Once you solve everything, you get the answer as 6.135 into 10 power minus 29 kgs. This is the mass. Okay, so this is how the same formula, only we are just rearranging it. Now second model question have come in the board twice, so you may get questions in that pattern also, where the kinetic energy is given. From there you will get the velocity, then you will substitute in the de Broglie relationship. Now we will get into the next topic, Heisenberg's uncertainty principle. We will be seeing about Heisenberg's uncertainty principle. Uncertainty. Certainty means we will say it is definite, that this can be possible. If it is uncertainty, uncertainty means cannot determine. I am not able to predict whether this will happen, that is called as uncertainty. That is uncertainty in weather. We don't know whether it may rain, or it may be cloudy, or it's going to be a sunshine, or today whether this Punjab will win or Rajasthan Royals is going to win. So this is what is uncertainty. You cannot predict what is going to happen. So Heisenberg's uncertainty principle was saying that it is impossible to determine simultaneously the position and momentum of an electron at the same time. What do you mean by simultaneously? See, I know this is my nucleus and I have definite path, circular orbits. If the electron is moving like this, if I know this is the position of the electron, but I cannot be able to know the velocity, with what velocity the electron is moving, or if I know this is the velocity of the electron, I will not be able to predict or say this is the position of that electron in the orbit. So simultaneously, I cannot say that this is the position and this is the speed, this is my velocity and this is the position. So if I know the position, I will not be able to find out the velocity of the electron. Or in other hand, if I know the velocity of the electron, the momentum of the electron, I would not be able to determine perfectly the exact position of that electron in the orbit. So that is what Heisenberg's uncertainty principle states. And he has given an expression, a mathematical relation for it. He says del x into del px is greater than equal to h by 4 pi. Why this expression is being given? Because we will just get back into the significance once we finish it. Del x was a delta we used to write for change. Any small change we used to mention this symbol del. Change in energy, delta E we put, remember children. So del x is nothing but change in position. Delta Px is change in momentum. And what is momentum? Mass into velocity. So you put delta mvx. In m, when you bring it down, it becomes delta x into delta vx is greater than equal to h by 4 pi, where h is the Planck's constant. Now there are some significance with Heisenberg's uncertainty principle. It was able to rule out the existence of definite path or trajectory of electrons, means he was not very sure that the electrons are moving only in these definite orbits. The electrons trajectory of, that is a movement of the electrons in different orbits with different velocity is possible, and that is also possible only for microscopic objects. At the macroscopic level, it will not be able to determine the position and momentum of the moving object. So these are the main significance of Heisenberg's uncertainty principle. They have given a small example with a milligram of object, how you can find out the velocity using the mass of the given object. So now we will be doing two problems based on Heisenberg uncertainty principle. Let us do the problems in uncertainty principle. First one is, a microscope using suitable photons is employed to locate an electron in an atom within a distance of 0.1 Armstrong. What is the uncertainty involved in the measurement of the velocity? So distance is given, that is the position is given, which is del x. It is given 0.1 Armstrong, which is 10 power minus 10 meter. So from the formula we know del x into m del v is equal to h by 4 pi. So we have to calculate the uncertainty in velocity. So del v will be equal to h by 4 pi into del x into m. Now substitute the values. You know what is Planck's constant? 4, and what is pi? That is 3.14. We know what is del x? 0.1 into 10 power minus 10, and mass of electron we also know it is 9.1 into 10 power minus 31. Once you substitute, you get 0.579 into 10 power 7 meter per second. If you want to move the decimal, you can put 5.79 into 10 power 6 meter per second. Both are correct. I hope you are able to follow this, children. It is already solved in your textbook, but for your understanding I am just explaining you step by step. The next problem is, a golf ball has a mass of 40 grams and a speed of 45 meter per second. If the speed can be measured with an accuracy of 2%, calculate the uncertainty in position. So they have given mass is 40 grams, which is nothing but 40 into 10 power minus 3, that is 40 by 1000, converting into kilograms. Speed is 2% of 45, which is 45 into 2 by 100, so you get 0.9 meter per second. Now we have to calculate the uncertainty in position. So del x is equal to h by 4 pi m del v, substituting the value of h, 4 pi, mass and velocity, you get the answer for the position, which is 1.46 into 10 power minus 33, which is much smaller than even the atomic nucleus, that is the position distance. So this is for the microscopic level, you know, children. So these type of problems that we get in our exams with respect to each principles or theory. Now we will be studying about quantum mechanic model, how this quantum mechanics have come, and then we will get back into Schrodinger's equation. We have done with our dual nature problems, Heisenberg's uncertainty principle, and we also was saying that there were few drawbacks with Bohr's atomic model. Is just because if you see the structure of an atom, see there is a nucleus in the center which is concentrated with positive charge, and you can see circular orbits around which the electrons keep on moving. See, this was Bohr's atomic model, that is his assumption of an atomic model. But that was a failure is just because he was not able to prove the dual character of a substance of matter, that is a matter having both wave nature and particle nature. Also, he was contradicting with Heisenberg's uncertainty principle, because as we learnt in Heisenberg's principle, we know if we know the position of the electron, if we are able to find out the position of the electron, we will not be able to find out its momentum. Or on the other hand, if we know the velocity of the electron, we will not be able to locate the exact position of the electron. So, if it is having a dual nature of both wave and particle, definitely there will not be any fixed orbits. So, that is why Bohr's atomic model was not a appreciating model, or it was not coming up with the other models. So, from then Schrodinger's wave equation was derived. It was Erwin Schrodinger who has given an equation with H psi is equal to E psi. See, this was his equation where H is a mathematical Hamiltonian operator. Once you solve this equation, you will get the value of psi, which will lead to a set of quantum numbers, which will lead to a set of orbitals and quantum numbers, which will be giving us the exact address of an electron, where, in which shell, in which orbital and in which subshell the electron is present. So, from the Schrodinger equation, we will be learning about 4 important quantum numbers, which has given rise to the information about the exact location of an electron. So, the first and foremost is the principal quantum number. Now, before getting into principal quantum number, if you think these definite orbits, instead of orbits, let us assume them as shells. Now, what happens in shells? See, we know, if you consider or compare this with an eggshell, we know the eggshell is an outer covering, inside you have an egg. So, we know that inside the eggshell definitely the egg is present. Similarly, around the shells or inside the shells, it is definite that 90% of the electron is present. That is, the maximum presence of an electron will be inside the shell. So, that is what is the information given by the Schrodinger wave equation. So, when you come to principal quantum number, so principal quantum number means that is a main quantum number, that is a major quantum number which is giving rise to the size and energy of the orbital. It is the principal quantum number which says which shell the electron is present, because we have studied that the number of shells we can find out from the given atomic structure. So, we know there are 4 important shells K, L, M and N. So, principal quantum number will be denoted by the symbol N, and it gives rise to the size and energy of the orbital, which means in which energy level the electron is present. So, that we can find out using the principal quantum number. We can also calculate the number of orbitals in a shell using the principal quantum number, that is n square. Say this is my K shell where n is equal to 1, so 1 square is 1. So, only one orbital is present in K subshell. If you take the second principal quantum number n is equal to 2, 2 square is 4. So, my second shell will have 4 orbitals. Now, third one, when you come to M, it is n is equal to 3, which is 3 square, that is 9. So, I have 9 orbitals in my third shell. So, this is how it will be giving us the information to find out the number of orbitals in a shell. It also helps us to find out the maximum number of electrons in a particular shell. Now, if we know the number of orbitals, as I told you, one orbital can take only 2 electrons to the maximum. So, that is being given out by the formula 2 into n square, where if I have n is equal to 1, so it will be 2 into 1 will be 2. So, my K shell has 1 orbital with 2 electrons present in it. So, the apartments are the shells, each floor is a shell, individual houses are my subshells, and the orbitals are my rooms inside, and the people who are living inside, maximum 2 will be the number of electrons. So, we would like to imagine, children, the whole shells, the number of shells K, L, M, N will be 1 floor in a whole apartment. Individual houses in each floor will be my subshells. Number of rooms present inside the houses, subshells will be the orbitals, and the electrons will be the people in each room. So now principal quantum number will be helping us to find out the size and energy, also the number of orbitals and the electrons in a shell. Now we will study about azimuthal quantum number. Azimuthal quantum number is denoted by the symbol L, and that denotes the orbital angular momentum. That is how the electron moves, because it is going to define the 3D shape of the orbital. We know the shells, now we have to know how many subshells are present in each shell, because I know the main shells are K, L, M, N. So now number of shells will be equal to the number of subshells. How should I find out? Now by the formula, for given value of n, L will be is equal to 0 to n minus 1. So if n is equal to 1, it will be 0 to 1 minus 1, which is 0. 1 minus 1 is 0. So I will get only L value as 0. So for given L value equal to 0, I give an alphabet S. So my K shell has one subshell, that is S. Now how will I find out for n value is equal to 2? For n value equal to 2, it will be 0 to 2 minus 1. 2 minus 1 will be 1. So here it will be for 1, it is P. So for S it is only 1, and here it is 1 and 2. So 2 are present here in P subshell. And third one, it will be for n value equal to 3, it is 3 minus 1, which is 2. So here it will be for 2, it is D. 0, 1, 2, 3 I have given as S, P, D, E, F. This we have already studied in our 10th standard. So here S will have 1 orbital, here it will be 3, here it will be 5, and for F it will be 7 orbitals, which we will study in the magnetic quantum number. So now we just need to know, for given value for L 0, 1, 2, 3, we have given an alphabet of subshells S, P, D and F. So with this, the azimuthal quantum number also gets over. Now we will study about magnetic quantum number and spin quantum number. We shall see the magnetic quantum number and spin quantum number. Magnetic quantum number gives us the orientation, that is the number of orbitals in each subshell. I told you we have shells, shells has got subshells, and subshells will have orbitals. Now those are the rooms in each subshell. How can we calculate with the formula 2 into L plus 1? For given value for L, you have the m value as 2 into L plus 1. Say if L is equal to 0, it will be 2 into 0 plus 1, which is 1. Right. So that 1 is nothing but for m value will be again 1. Okay. 2 into 0 plus 1, that is 1. If L is equal to 1, it will be 2 into 1 plus 1, which is 2 plus 1, 3. So we have 3 values here ranging from minus L to plus L. So we have minus 1, 0, 1. Children, please understand, for my L is equal to 0. If L value is equal to 0, it is my S subshell. So S subshell, we have to find out how many orbitals will be present. So for L value is equal to 0, formula is 2 into L plus 1, 2 into 0 plus 1, which is 1. So that for 1, we have only 1 orbital, no other orbital is present. For L value is equal to 1, which is my P subshell, I have to calculate how many orbitals are present. So for that, it is 2 into 1, which is 2, plus 1, that becomes 3. So how many values will be there? It is actually from minus L to plus L. So since it is 3, so you get minus 1, 0, 1. For L value of 1, it is minus 1, 0, 1. So you have 3 orbitals here for P subshell. And for D, for L is equal to 2, it is 2 into 2, 4 plus 1, 5. So you have 5 orbitals. I need 5 values, which is minus 2, minus 1, 0, plus 1 and plus 2. Depending on the L value, you will have minus 1, 0 and plus 1. Okay. Similarly, for L is equal to 3, which is my F subshell, it is 2 into 3, 6 plus 1, 7. So, I should have 7 orbitals with 7 orientation values, which are -3, -2, -1, 0, 1, 2 and 3. So, this is how we calculate the M value for the given L value. Now, the last one is the spin quantum number. Spin quantum number helps us to find out the spin angular momentum. That is, we know the electron has its own axis, spin around its own axis and also around the nucleus. So, there are two types of spinning possible. One is a clockwise direction, the other one is an anti-clockwise direction, for which we give two values +½ and -½ for the rotation that it does on its own axis. So, since we know in an orbital the maximum number of electrons that can be accommodated is only 2. So, we have 2 electrons, where to put those spins we put as an up arrow and a down arrow to represent the two opposite signs, that is +½ and -½ If there is only one electron, you put either +½ or -½ depending on the arrowhead. Either it is an up arrow or it is a down arrow. So, these are the 4 important quantum numbers given to us for this year, and after this is over you have 4 important postulates given to you regarding this basic quantum numbers, that is principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. So, I want you to go through that. Once you study that, you will be seeing a video now along with this to study more in detail about the shape, orientation and also the information about the 4 quantum numbers. So, with this we will wind up the class for today, children. We will be learning about the energy of these orbitals and rules for filling the electrons in the orbitals in the next class. I hope you enjoyed the class, you are able to understand. If you have any doubt, don't hesitate, children, kindly call me. Take care, stay home, stay safe. Until then, see you in the next class. Bye.
Quantum numbers. The space around the nucleus where there is maximum probability of finding the electron is called an orbital. The electronic orbitals associated with a particular atom have different orientations, shapes and size. In order to determine the position of electrons in an orbital, a set of 4 numbers were identified. These numbers are called quantum numbers. The 4 quantum numbers are principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. Click each tab to learn more. The principal quantum number represents the main energy level in which an electron is present. It is represented by n, where n takes the value of a whole number such as 1, 2, 3, 4, 5 and so on. The principal quantum number of an electron gives an idea about the average distance of the electron from the nucleus and the energy of the associated shell. Greater the distance between the shell and the nucleus, greater is the energy of the shell. The azimuthal quantum number determines the angular momentum of an electron. It represents the subshell associated with the main shell. The azimuthal quantum number is denoted by L. The value of L ranges from 0 to n-1, where n is the principal quantum number. The different values of L or the subshells are represented by the letters S, P, D, F and so on. If n is equal to 2, the value of L is 0 to n-1, which is equal to 0 to 1. Thus, the second energy level has 2 subshells, namely the S and P subshells. Thus, for n equal to 1, there is only one subshell S. Similarly, For n equal to 2, there are two subshells, S and P. For n equal to 3, there are three subshells, S, P and D. And for n equal to 4, there are four subshells, namely the S, P, D and F subshells. As mentioned earlier, the azimuthal quantum number also determines the angular momentum of an electron. The magnetic quantum number determines the number of orbitals associated with a subshell. It is denoted by ml. The value of ml depends on the value of the azimuthal quantum number L, and its value ranges from -L to +L, including 0. For L equal to 0 or the S subshell, the value of ml is 0. The S subshell has one orbital called the S orbital. For L equal to 1 or the P subshell, the values of ml are -1, 0 and +1. This subshell has three orbitals called the p orbitals. For L equal to 2 or the D subshell, the values of ml are -2, -1, 0, +1 and +2. This subshell has five orbitals called the d orbitals. For L equal to 3 or the F subshell, the value of ml is -3, -2, -1, 0, +1, +2 and +3. The F subshell has 7 orbitals called the F orbitals. In this way, the total number of orbitals for a given value of L is equal to 2L plus 1. The spin quantum number determines the spin of the electron around its own axis. It is represented by ms. The electron can spin around its axis either in the clockwise or the anti-clockwise direction. There are only two values of the spin quantum number, +½ or -½ This value is independent of the values of other quantum numbers. Choose the correct orbital designation corresponding to the quantum numbers n equal to 4 and L equal to 2. Select the correct option and click Submit. Which of the following sets of quantum numbers is not possible? Select the correct option and click Submit. Choose the possible number of values of ml for L equal to 2. Select the correct option and click Submit. Let's quickly summarize quantum numbers and their determination.